Welcome back for this second part of the first lecture. The goal we are going to look for is the statement of the main result by Chen and Chen. Okay, so we need some definitions and notation. As we said earlier, for us N, J, G, we always stand for a compact, smooth, Kähler manifold. And while the complex structure is gonna be thought of as a fixed one, G will be varying within the Kähler class. So corresponding to this triple of data, we have omega defined as the Kähler form of G, and capital H, the functions of regularity for alpha with real values, for which omega plus partial bar phi is positive definite, and whence it gives again another Kähler metric omega phi, which is homologous to the original one. And this capital H is the Kähler class. Why the regularity for alpha? This is because the equation is a fourth order elliptic PDE, and this 4 here reflects that fact. Now, for each omega phi in the Kähler class, confusing phi with omega phi, so we can abuse the notation and write like this. Let capital R of phi be the scalar curvature of omega phi. So phi is the contraction of Ricci, the Ricci tensor of omega phi. So the question is, does there exist phi tilde in H such that R phi tilde is constant? The CscK problem. in case that constant would be equal to the integral of R phi on the volume form induced by the metric omega phi and over the volume of the manifold respect to omega phi. Because of cohomologous argument, which are very basic, the numerator of this fraction does not depend on phi, just as the numerator of this fraction. So these numbers are given by the initial data. Okay. Now we have to recall slightly different notions. The space H can be endowed with Finsler structure. This way. So we can consider the tangent space to the Kähler class at any point, and this is gonna be isomorphic to the C for alpha functions with real values. Okay, then take an element Xi in the tangent space, and we define its norm as the L1 norm integrated with respect to the volume form induced by omega phi. This is a definition introduced by Tamas Darvash. And then given a smooth curve alpha from 0, 1 to the Kähler class, we can compute the length as the integral of this norm of the push forward of alpha at alpha. Now pick phi0, phi1 in the Kähler class. One could define the infimum of the length of C1 curves connecting phi0 and phi1. And the question is this a distance? Actually, the symmetry of this definition is easy to prove, as well as the triangle inequality. And the tricky part is this inf is positive. I mean, if this inf is 0, if and only if these two Kähler potentials phi0 and phi1 are the same. And the theorem by Darvash, building on a previous result of Shuzhong Chen, D1 as defined as the infimum of length of curves for that norm is a distance. The D1 distance. Okay, since we introduced the tangent space to the Kähler class, we can also recall the definition of K-energy functional. Is a functional K from Kähler class to R such that it's pushed forward at some element of the Kähler class in a tangent vector is minus the integral from m of m r phi minus r omega phi to the n. Okay, so this definition is by means of the differential form of the functional. Why is that important? Important since its critical points are CscK matrix. Okay, this is actually, this R underlined is the constant we computed before. So this is the integral of R omega n over n factorial over the integral of omega n to n factorial. Constant. And we see from this very definition that the critical points of such functional are precisely CscK matrix. Now we recall an expression of K rather than on of this its differential. Then, so the structure of K at some Kähler potential is entropy of phi plus another functional called J functional of Ricci. When we do not write the subscript here, it means that the reference metric is the initial, the given one. One could write omega, but we just avoid writing anything of omega. So we see that the structure of the Kähler energy splits in two terms. One is the entropy and one is this J functional. So the entropy actually depends on omega phi, which means if we add, that is entropy of phi plus c equals to the entropy of phi. And its definition is entropy of phi is the integral of m of the logarithm of the ratio omega phi to the n over omega n integrated with respect of the volume form of omega phi. Okay, so this is quite self explaining why this is an entropy. We can multiply and divide by omega n, and this is actually has the form of integral x log x, sort of, which gives a justification of the name. Let's move to the definition of the J functional. While given key closed, declosed one form, then J key of phi is 1 over n factorial integration over n of phi sum k from 0 to n minus 1 key wedge omega to the k wedge omega phi to n minus 1 minus k minus 1 over n minus 1 factorial integration over n key average phi sum k from 0 to n omega to k wedge omega phi n minus k, where it takes only to explain what's the average of key. Is the ratio between the integral over m of key wedge omega n minus 1 over n minus 1 factorial over the integral of omega to the n over n factorial. Well, we remark here that the Euler-Lagrange equation for J omega is trace of omega phi of k is the average of k. So earlier we said that the Euler-Lagrange equation of the k energy is the CscK equation. Here, without deriving it, we just we state the result, the fact that the Euler-Lagrange equation for the J function is this equation that will be that will come back also in the future discussion. The next definition normalized Kähler class H0 are those potentials in the Kähler class such that the integral over m of phi times the summation from 0 to n of omega k wedge omega phi to the n minus k is 0. Okay. Now we want to define the properness of K energy. And we see how the ingredients introduced so far comes together into the picture. And the properness of K energy can be defined for a general automorphism group, and this is done by Chen and Chen. Is defined by Berman, Darvash, Lu, and the result by Chen and Cheng also considers that definition of properness, but to consider a simpler case at the beginning, we suppose that the identity component of the automorphism group, so the holomorphic biholomorphisms, the biholomorphisms of M is trivial, namely out 0 mj is trivial. Okay, so the properness of K energy under this condition is there exists a sequence of Kähler potentials phi lambda normalized with limit for lambda to infinity of d1 0 e lambda plus infinity if if the sequence does this, then the limit for lambda that goes to infinity of the K energy evaluated at phi lambda is also plus infinity. Okay, then the theorem is the properness, and now we state the main theorem. This is the theorem labeled as 1.3 in the second paper of the series that I linked to in the reference list for this mini course. Assume that the identity component of the biolomorphisms group of M is trivial, then there exists a CscK metric in Kähler class if and only if the K energy is proper with the definition used before. The definition of properness, we saw the normalization condition and the d1 distance. So a couple of remarks before concluding. This was proved is the achievement of Chen and Chen, while the other direction was proved by Berman, Robert Berman, Tamas Darbash, and Qin Lu. So our next goal is for the second lecture tomorrow is gonna be to describe the strategy used by Chen and Cheng to get this achievement. And thanks for your attention. Have a good day.